Hopefully from your previous classes you're familiar with the concept of phasors, and what we've shown you in the past is the phasor technique, where we'll write a sinusoidal voltage, V peak cosine of omega t plus phi, and we will write the phasor version of that as V peak at angle phi. Sometimes we'll write it as V RMS at angle phi. And I've proven this to you in previous classes, and this is called the phasor. And these two forms are called the phasor form. And by performing what we call the Phasor Transformation, which is just changing this to this, we can analyze circuits without having to continuously write the cosine form of this periodic signal. However, this transformation here becomes problematic when the periodic signal has two independent variables. So here we've only got one. In the traveling wave, remember, we have two independent variables, and so this phasor transformation doesn't make as much sense. And I'm going to show you how we utilize the phasor form for EM waves in this course. To do that, I'm going to start with the concept of e to the j theta, and all I've done here is take a value for theta in degrees, and I've run it from 0 to 180 in different increments here, and then I've calculated e raised to the j times theta and put some values here. And if I were to plot these values, remember, in the real and imaginary plane, this is your imaginary axis and this is your real axis here. And so 1 plus j0 puts you about here. 0.966 plus j.259 puts you, about right here. 0.707 plus j.707 puts you here. 0.259 plus j.996 puts you about here, and 0 plus 1j puts you up here. Minus 2.59 plus j.966 minus 0.707 puts you over here. Minus 0.966 plus j.259 puts you over here, and minus 1 plus j0 puts you over here. And you see, my drawing's not that good, but if we were to continue this, we'd get a circle with radius of 1. And e to the j theta is just another formula for what we call the unit circle. And so I've used some software to produce a better looking unit circle, and the point that I want to make is that any place on the unit circle, I can dissect that point down into two components. We've got the r cosine theta of that point, and we've got the r sine theta of that point. So the x position is equal to r cosine of theta, and the y position is equal to r sine of theta. And that's just from basic trigonometry, right? And the r is there because this isn't any longer a unit circle, it's any circle with radius r, right? And so what I would say then is that the location of any point on a circle can be written as x plus jy, right? That's just the x value of that point plus the y value of the point, x plus jy. And so I could easily write that as r cosine theta plus j r sine theta. Well, over here I demonstrated that e to the j theta is also the location of any point on a circle. So we could make the substitution r e to the j theta is equal to r times the cosine of theta plus j sine theta. And this here is, if you divide the r out of that equation right there, is called Euler's identity, and it's just e to the j theta is equal to cosine theta plus j sine theta. And we call the cosine portion of this the real portion. We call the sine portion of this the imaginary portion. And we can use Euler's identity to represent a traveling wave to do the following. So let's start with the traveling wave. V of x comma t is equal to Vp cosine of omega t minus beta z. We're going to include our phase shift phi for this one. And in this case, this whole argument is just what is theta in there. And we can then write V of x comma t is equal to the real portion of Vp e to the j theta. And that comes directly from this right here. So if I were to write that, if I were to do the substitution, it's the real portion of Vp e to the j omega t minus beta z plus phi. All I've done is substitute in for theta here into the exponent. Typically for convention, we'll drop this real portion and we'll just write v of x comma t is equal to Vp e to the j, and we can distribute omega t e to the minus j beta z e to the j phi. And I just used the dissociative property here in the exponential to separate those out to three different terms. And typically we will write v plus is equal to Vp e to the j theta, and that corresponds to the phasor you're used to writing, and we call that the fixed phasor. And a lot of times that's given a little bar over it, and it is equal to V at angle, well, in this case we've been using theta, not phi. V plus e to the j phi is just equal to V at angle phi. We let e to the j omega t, we call that the time phasor. And then the last part of it, e to the minus j beta z, we call that the distance phasor. So in electromagnetics, phasors have three parts: the fixed phasor, which is the peak value times e to the phase shift. It's the same as what it was in previous classes. We've got the time phasor, e to the j omega t, and we've got the distance phasor, e to the minus j beta z. A major advantage of using this form of the phasor technique is that it makes taking derivatives and integrals much easier. And you might remember from calculus that the derivative with respect to x of e to the x is just equal to e to the x, and the integral of e to the x with respect to x is just equal to e to the x. So if we were to take the derivative of e to the j omega t just with respect to t, we would just have to take the derivative of the exponent. The derivative of j omega t with respect to t is just j omega, and then we would multiply it by e to the x. And similarly, the integral of e to the j omega t is going to be 1 over j omega e to the j omega t. And this is a very powerful tool in electromagnetics, as is the phasor representation of the voltage, current, electric field, or magnetic field.